At Maxar, we turn big ideas into successful missions. Missions that address change on Earth and power exploration into our solar system and beyond. And over the last 60 years, Maxar has helped visionaries, big and small, look for new ways to understand our planet and move humanity forward. Maxar's space infrastructure capabilities harness the promise of space for programs like in-space robotics to explore distant surfaces, power and propulsion systems that will propel us further into the galaxy, and communications satellite that provide connectivity across the globe. Our Earth observation satellite technology is revolutionizing how we identify, understand, and predict change at speed and scale. Maxar helps make space accessible, global change visible, and information actionable, all for a better world.
Welcome back to the APSCC webinar series. I'm Christopher Slaughter, your MC for the series. Today, the subject is new technologies in HTS systems. It's brought to you today by Maxar. We're very delighted to have their support for the ongoing webinar series. They're also the registration sponsor, so thank you, Maxar. Today, ArgoSat's Graham Shaw is the moderator of the session. Hampton Chan from Maxar is one of our featured speakers, as is Stuart Dottridge from Kratos, and Francis Selvados from Hughes. Please take it away, Graham.
Good evening, and welcome to our panelists. We're going to talk about HTS today and about new technologies and advanced technologies in HTS across both satellite and ground. And we've got a distinguished panel here. My name's Graham Shaw. I'm a consultant, industry consultant, also an investor now, recently a private equity investor. We have Hampton Chan from Maxar. We have Stuart Dottridge from Kratos, and Francis Salvados from Hughes, HNS. I think it'd be worthwhile just to set the stage, just if each of you could introduce yourself a little bit and talk about your role within your companies. I guess we'll start with Hampton.
Okay, thank you, Graham. So I am from Maxar, and I'm the Vice President of Mission Engineering. I've been with former SSL and currently Maxar for a total of more than 25 years. And my current role is working on the software-defined satellite project, and among other activity, in general, system architecture and supporting business development, and as well as program implementation in my past. And I am honored to join this panel here today.
Okay, Stuart.
I am Stuart Dottridge. I'm with Kratos, and let's see, I've been with Kratos for over 20 years now, and I'm currently the Vice President of Advanced Technology, which basically means that I'm looking at the what our development roadmaps, and particularly where we want to be 2, 3, 4 years out, from a design and architecture point of view of our product lines.
Great.
Hi, I'm Francis. Thank you for having me participate in this conference. My name is Francis. I'm a Vice President responsible for all the systems and solution engineering in Hughes. I'm responsible for all the systems and product sales for all the international region. We have a separate group which does North American division, but for all of international, I'm responsible for systems and product sales.
Great. So, I've got a bunch of questions to ask, and we'll have a kind of a free-for-all discussion. Feel free to jump in if you've got something worthwhile to say. Well, anything actually to say on any of these subjects. You certainly don't have to wait for me to ask you, but my first question, given the subject matter about the next development in HTS, is really for you, Francis, and HNS.
Yeah.
We know that, I think a lot of people know that you've got several spacecraft in orbit, and the next spacecraft that will be launched by HNS is a totally new generation Jupiter 3 spacecraft, which will be, as we understand it, an enormous spacecraft. So I just wanted to ask you, a little bit about J3 and about what were the key drivers around that's next generation, and what were you looking for, and try and phrase it in the way of the technology side of things.
Yeah. So I think the J3 was built to meet the strong demand for market. Today we serve entire Americas, right? We started with North America way back using Spaceway 3 that had a full corners coverage, but that was really not a broadband service. It was only offering 512 kilobit service.
Right.
But then we realized that we need HTS satellites. We started with Jupiter 1 that offered about 150 gigabits. And then we went to Jupiter 2 that offered close to 200 gigabits. And then we also contracted with Eutelsat for a capex deal to buy the entire capacity over Brazil using 65 West. And then we contracted with Telesat and bought all of their T19 capacity.
Yeah,
that's Ka-band capacity over Latin America and Brazil. In fact, recently we did a deal with Telesat and acquired even the Caribbean beams. So if we combine all of these 4 satellites, we get a total capacity in excess of 500 gigabits. Now, when you look at the growing demand in our markets, if we have to meet, because most of the beams are already filled, and
the busy ones are, right? The busy ones are filled always.
Right. And the beams which are not built, you can see that it is about to get congested. So we are very thirsty for capacity. So if we have to build another satellite, we need a capacity scale in excess of 500 gigabits. Knowing that if I look back 5 years, 7 years, our market has evolved, and we have seen the growth rate and the capacity demand in the last 5 to 7 years. And we see a foreseeable growth in these markets we saw today. We cannot go anything below 500 gigabits. That's the key driver, and that's the key motivation for Jupiter 3. And then there are 3 factors we considered the most while deciding the Jupiter 3. One is the capacity. We can get as much as capacity as possible using a single slot and using a single satellite. And the other factor is the capacity density. If you look at a lot of beams, which gets filled when we launch a satellite and go into service, is this is semi-urban or this small people who lives in semi-urban areas. Like if you look at the beam over Washington, D.C., when we launched J2 service, when satellite went into service, the first beam to get filled was this beam over Washington, D.C. It's surprising. But in those areas, the cable and the fiber guys, they don't make an investment because they don't see that economics, they work.
Yeah.
So for us, the capacity density is another important factor to consider.
I think it's a key thing to understand for
right. And then obviously the cost per bit is the most important factor, right? So the more you lower the cost per gigabits, you'll be able to give a better quality of experience for a given ARPU. So those are the 3 factors, the 3 things we focused on.
I think the density.
So based on the existing market we saw, knowing where the subscribers are and what the subscriber density is, we know exactly where to put capacity, and we know where to put how much capacity in a beam. So that's the reason we decided that we will build a 500 gigabit satellite.
So it's, I just want to restate. So it's not that it's 500 gigabits, spread out. The real challenge here appears that, or not the challenge, but one of the innovations is that it's recognizing that the capacity demand is reasonably concentrated around the areas that have high demand, which is usually suburban regions, right? It's where there's enough people. It's where there's enough people that can buy the service, but it's not dense enough that there is fiber to the home, or cable, cost-effective cable. And so it's these kind of suburban regions, but they're reasonably small in geographic area, so you need a high density as opposed to just size. So with that in mind, turning over to Hampton, how did, with those kind of drivers that Hughes wanted, the big spacecraft in terms of total capacity, but the high density, what did it mean for the design effort, and how did Maxar go about building this spacecraft?
Yes. So first of all, Maxar is very proud and honored to have been the manufacturer for delivering those 4 satellites that Francis has mentioned, starting with Jupiter 1, Jupiter 2, and then Eutelsat 65 West and Telstar 19B. And then we are currently working on the Jupiter 3. And as Francis mentioned, that it is a very high throughput satellite. Not only that, but it's also servicing ultra high density in some of these capacity over a small geographical area. So it's a very challenging overall design problem a few years back, but I think we at Maxar had a series of internal research and development projects over the years prior to the Jupiter 3 start of the project that helped us to be prepared, to be well positioned to provide some of these features that are required. So the key features that are required to design and deliver such a ultra high density HTS system includes miniaturization of electronics, because you have to have a lot more electronics to go with the higher capacity in general, and conventional technology in terms of packaging and all that just not going to work. You don't have enough volume and footprint to do it that way. So that's one key element. The second one is the high efficiency amplifiers. In this case, we have a subset of those applications is actually driven by solid state power amplifiers. And so we took advantage of some of the internal research development effort that have been going on at that time and applied that technology to help us generate a highly efficient design.
Are those gallium nitride?
Those are gallium nitride, yes, right? And then another key enabling technology is the high efficiency antenna systems, because in order to pack ultra high density in a small area, you can imagine that you have to have small spot beams and you have to have tight control and all that. And then also it's a transmit subsystem by itself to facilitate a fairly large radio frequency transmission out of that design as well. So an integrated thermal subsystem, it's also a crucial enabling feature. And then another element is, related to Hughes' acceptance of going to Q-band and D-band spectrum for the gateway feeder lanes. And this is an attempt to basically free up more of the Ka band spectrum strictly assigned to the user lanes, right? So, and prior to Jupiter 3 program, Maxar, we actually have also invested a lot of effort working both internally as well as with outside suppliers to qualify the Q-band and D-band hardware that can be deployed as a flight production environment. And as a matter of fact, Jupiter 3 is going to be the first satellite to have real Q-band and D-band gateway link operationally, as opposed to a demonstration or just a small subset of the entire.
And I'm familiar with the qualification programs of QV band transponders, and it's been challenging, I think, getting the operational data. So it'll be interesting to see that when it launches. We'll come back to QV band later when we talk about Asia, because I think it has some relevance to the Asian market about how we deal with that in Asia. So in terms of will it be the biggest spacecraft in terms of power and things like that that Maxar has ever built, or is it in family with some of your other your large spacecraft?
In terms of power, it is in family with the biggest DBS satellite. You can imagine that the direct broadcasting satellite, it's also, at that range, right? The Jupiter 3 satellite, it's roughly at, the 25 kilowatt end of life DC power range. But it is a very heavy satellite because of all the components that are required to support the high throughput, ultra high density mission.
A lot of equipment, right?
That's right, all the equipment count. So even with all the miniaturization, it is still a fairly heavy satellite.
Right. Now, I was going to say, a lot of operators these days have been putting their focus for several good reasons on instead of building enormous throughput satellites, they've been focusing a lot on flexibility and building smaller geo satellites with around 100 gigabits or 150 gigabits with flexibility. And I know that at Hampton you're working on that project within Maxar anyway. And this is a question for kind of almost everyone on the panel really, but especially HNS and Maxar. How do you see the balance of importance between flexibility, which is what we're seeing kind of the hot, it's what a lot of people talk about at the moment, versus kind of pushing down the cost per bit curve and as we talked about, capacity density, which is kind of how you make money, how the operator should make money at least. How do you see the relative importance there?
So, that we have seen a lot of the satellite manufacturers came and talked to us and made a great deal of how important to consider flexible satellite. And flexible satellites are really fascinating. We think the flexible satellites are great assets for markets where the demand is uncertain or it has a lot of variability. For instance, if we consider aero or maritime services, the market demand is uncertain, knowing, there are a lot of airlines goes out of business, or there are new airlines comes, the route of changes, the markets they are serving is different. Your capacity demand and your coverage requirements are constantly changing. So flexible satellites are a great asset to address that kind of market. But one thing we have seen is that with flexible satellites, the other factor that flexible satellite helps is there are certain markets where you have unpredictable regulatory and policy changes. So if you have a country where it says that you need to have an in-country gateway, and if you're designed like a Jupiter 3 system where you're designed in a very specific way, and all of a sudden you decide that if you want to enter into a new market and that enforces you to have an in-country gateway, probably flexible satellite will help. So it's for very specific markets. So as long as you know what you need and where you need the capacity, you can stay with the Jupiter 3 class satellite. But if you don't know, don't know the markets very well, and if the market demand is uncertain,
and the flexible satellite makes sense. And so how does that, rolling into the next question, how does that pertain to Asia Pacific, the Asian market, where, we do have a lot of emerging markets, a lot of growth, and a lot of fragmented national operators, lots of different operator companies. Do you think that the ultra high density approach could work? And to do so, would you have to kind of form partnerships between operators, or is the flexible satellite, you think, a more applicable approach?
So the high density approach works in certain countries. For example, if you're asking about specifically for Asian market, probably high density approach works for countries like China, India, and Australia. The reason is you have enough addressable market, and there's plenty of opportunity there where you need a 200 plus gigabits like satellite. But there are a lot of countries in Asia Pacific you have seen where the markets are so fragmented that that limits you to serve in only one country. There, probably the HTS, you don't see that there's, a lot of these countries probably may not need this 200 plus gigabits HTS satellites. And those markets probably can be served either by a medium throughput like 30 to 100 gigabits type scale satellite, or probably there is a market for flexible satellite that can address the market. But also you have to remember these markets are also very sensitive to price. And if somebody can build a flexible satellite without any cost escalation, I think the operators probably would consider flexible satellites seriously. That's our view. But there are also a lot of great benefits they can bring. For example, if somebody wants to serve a specific country as well as the neighboring countries, and if they can form partnership, and the flexible satellite allows them to move capacity to this neighboring country when it opens up, they would prefer to consider a flexible satellite. But I think a lot of these countries, as I mentioned, China and Australia, probably HTS is a better fit. As long as you know where you need the capacity and what the capacity density needs are.
Okay. So it sounds like,
having said that, we know that one of the operators is considering using a flexible satellite to address both DTH and broadband market. That's an interesting thought. We have been talking to this customer of ours, and that's an interesting thought to look at it. Why they have taken a subscription.
Especially as the market evolves, right? As the DTH market kind of degrades or declines over time. You
exactly
start with an HTS. I start with a flexible satellite and address the video market and migrate over time towards the data services.
Broadband,
that makes a lot of sense. It's a good risk reduction. I think Stuart's been sitting here, and I've got some questions for Stuart now. So now we've talked about the technology on the satellites, but how has the ground systems had to evolve to keep pace or even move ahead, I suppose, of these new spacecraft, and whether it's the high density spacecraft or the flexible satellites or anything in between? Oh, there you go.
There we go. So I think the key takeaway is two things. You have a ton of innovation that's happened on the satellites, and what's driven that is the fact that satellites now need to support IP data transport instead of a broadcast applications. And so when you start looking, now the problem is ground systems have not kept up with the innovation on the satellites. And, but you're starting to see that innovation happening on the ground. And it's really, starting to apply, some of the technologies out of the telecom and cloud world into satellite ground systems. But the two key things you got to look at that you need from the ground system for these ultra HTS satellites or software-defined satellites is that, one, you need the ground system to unlock the capability of the payload. With some of the software-defined satellites that have been launched to date, they get it in orbit and have this incredible flexibility on the satellite, but they lock it down because the ground system can't find a way or doesn't have the capabilities to support that flexibility, and it doesn't have a way to monetize the payload's capability. So that's one big challenge. And when I say monetize the capability, it's got to be able to use it in such a way that it lowers the cost per delivered bit and/or improve the end user experience.
Or address more customers, right? I mean, it's no good having the ability to reallocate bandwidth capacity between beams if you've got no means of knowing the demand in that beam and allocating it through a feedback loop with the ground system.
Yeah, and at the speed and rate that the data traffic is changing.
Yeah.
The other problem we see with ground system today is the cost models are too high. And what I mean by that is, if you look at the capex required for a ground system for a software-defined satellite or an ultra HTS satellite, it's almost as much as the satellite. And then when you start looking at the total life cycle cost, it's pretty high. And one of the real problems is that since the hardware, most ground systems right now are built with purpose-built hardware, you got to deploy a lot of that hardware day one before you go into operations, even though you may not fully utilize that hardware for years. And that just from a business model, really cost inefficient. It drives up your cost per bit. And so what we see is that as you move to more, the 5G model where you go to virtualized network functions and you move away from purpose-built hardware, it's going to enable new business models on the ground system side that allows you to way more efficiently use your capital for the ground, cost infrastructure, because you won't need to deploy so much hardware and you can deploy the software as you need to ramp up your services and therefore your costs will be much more closely tied to your revenues. And so bottom line is I think the satellite payloads have done, and the satellite manufacturers have done a great job advancing the satellite payloads, and the ground system now needs to, it's their turn to step up.
I mean, there's a lot of talk. I know that I've looked at Crysis' website, and it's excellent for those who want to look at advanced ground systems. There's a lot of educational content there. And I know that you talk a lot, or your company talks a lot about digitization of the ground system there. I think that's one of the things here. You mentioned, network NFV, network
virtualized function.
Virtualization.
Yeah, network. Yeah, exactly. And I think that for some of the people watching, they may not be familiar with what that involves. So I don't know if you want to give a brief introduction of what it means to move away from kind of bespoke hardware solutions toward a cloud-based solution or an NBF.
Yeah, so basically the idea is the concept is you want to digitize the signal once, and you want to do that as close to the antenna as possible. And then you want to basically do all of your IF data routing and all your signal processing in software. And ideally, you want to do that with software that runs on generic, x86 compute hardware. And then you can put that software in containers, and you can basically orchestrate the software using cloud technologies to deploy, modify, operate, and tear down the virtual network functions. And this isn't new technology. The telecom industry is doing this today. This is one of the key things about 5G technology, is all about orchestrated virtualized network function to give them greater flexibility to, give you the bandwidth you need when you need it, and to be able to use software-defined networking to, in real time, bring up services, tear them down, and optimize them. And so really it's just applying that technology that that's come out of the terrestrial world and the cloud world, and apply it to satellite ground systems. And so basically, your modems, your switches, your combiners, all that become software functions. And that
presumably makes you more future-proof as well. It allows you to upgrade to different things, and it simplifies the interface with the satellite controllers on the satellite network in terms of dynamically allocating the capacity and things like that. Presumably, it simplifies a lot of that control plane as well.
Absolutely. And it allows you to look at new architectures, and because now your signal processing doesn't need to be tied to your antenna, and it changes up and gives you a lot more flexibility and options than you ever had before. And now, as long as you have generic compute, you can deploy a service, and what that service is can change very quickly. Right. So you see this, where this has really been deployed in the satellite industry is in the Earth observation market, where, you see ground system as a service all over the place, because, we've been able to take TT&C and mission download modems and move them into software. And so now, the data products of the EO market have always been produced in clouds, whether it be private clouds or public clouds. But now you've been able to move your signal processing and your downlink mission data processing into that same cloud, which allows them to actually, get from downlink data to data products that they can push out to customers faster. And that creates real value for them. And the other thing is, 10 years ago, if you were putting up an EO satellite, you had to put up your own ground system.
Yeah.
Now, no one would even consider that,
no one
because why would you? You got 5 or 6 different companies that all offer a really good service.
Right.
So
that you mentioned several things during this recent discussion just now that I want to hit on and bring in the other members of the panel. And I'll kind of go through them. The first one was you talked about how the ground system needs to enable the flexibility on the satellite, or needs to enable the capability of the spacecraft. I have firsthand experience seeing this, where a satellite operator client of ours has a flexible spacecraft, but they are struggling to know how to benefit from that flexibility within the constraints of their standard operating procedures, in terms of how they're used to operating the BOSS, the business operations software that they're very familiar with and they're comfortable with, and the ground network that whether it's the gateways or the hubs, and also the satellite controllers, and that whole interface between groups that traditionally didn't have to interface completely flexibly and transparently. And so this is a question for all three, because all three of the panelists here, because it affects all three of your businesses. From an operator standpoint, like HNS, how do you control your operations in a way that you're getting the benefit of the capability of satellite? How does the ground network make sure that they're providing what the satellite network needs to provide that? And how does the satellite network have to design the hooks that the ground network can control? How does that mesh of interactivity work? And when should the cooperation take place? Should it take place from the very design phase? Is it something that can be done after the fact? Because I don't know the answer. I know the different software pieces, but I'm not seeing it work in practice at the moment within the confines of a company.
Yeah. So when we designed the Jupiter 3 series ground system, that originally it was intended for our Jupiter 3 satellite. So fundamentally, we embraced a different architecture for Jupiter 3. The primary reason is because of the use of Q and V band, as Chan mentioned. So when we use QV band, one of the challenges that because of the weather-related issues, there will be a frequent switchover happens amongst gateways, and so that means that may result in a lot of this user connection interruption. So we have to embrace a different architecture. We call that centralized. So what we have done is that we, in the Jupiter 3 ground system architecture, all of the modem equipment, we call that as an RF gateway. That is located right behind the RF terminal. And then we have got a high-speed fiber link that is connecting it to multiple data centers. So then we used the SDN feature to orchestrate not only the networking components, but also the functions such as schedulers and bandwidth managers and all of that can be orchestrated using SDN feature. So we did not require a close association with how the payload behaves. It's entirely up to the ground system to decide how the signal flow happens, because at any point of time when you switch between different gateways, the forward channel processing and the return channel processing signal flow constantly changes, because this forward channel, return channel processing, schedulers and bandwidth allocation.
Are there people in the loop there, Francis, in terms of the SDN and as you said, the like a gateway change? If a gateway becomes impaired for rain or anything, and there needs to be a gateway change, how is that orchestrated? Is it manually done? Is it automatically requested? And how does the SDN?
We use quite a bit of machine learning and artificial intelligence to determine the necessity for changeover in real time, and then we orchestrate. So it's not done manually, everything is automatic. And because it uses the centralized architecture, when the gateway switches over, as suppose the gateway is failing and another gateway is taking over, because we centralized all the data processing, the user connections are maintained. And so all this switchover appears very seamless to the user. They don't lose any connections. So they continue to do the browsing. And when the switchover happens, sometimes they will see a slight buffering. They're watching a video, or if they're browsing, it pauses for a minute, but they don't see like an interruption in their connection. But all of this orchestration happens automatically.
So Hampton, how does that, based on what was just said, does that result in design drivers, or does it result in required design changes with respect to the satellite or the control software for the spacecraft? I mean, how do you interface with the system resource management, or is there any specific changes that you have to make?
We have not done that for the Jupiter 3 satellite, but remember that the Jupiter 3 series ground system, also we have signed 2 contracts with the 2 of our customers. One is for HTS 17, which has a flexible payload. And then recently we signed another contract with Eutelsat VHTS. And there what we have done is we have created an API that can talk in real time with the payload resource management system. And so the payload resource management system, they call mission segment, that orchestrate the changes to the satellite payload as well as to the ground system. So we have developed a special API so that we can make the ground system configuration changes in real time.
And so Hampton, does your design effort really involve interfacing with that payload resource manager? Is that the interface point?
Yeah. So to add to what Francis and Stuart had mentioned, for software-defined satellite or flexible satellite in general, when you have a very capable payload that could be reconfigured to suit your business needs, you do need to think about how to help the operator to properly configure it in a dynamic way to realize those benefits, right? So for Maxar, we definitely are not just designing the satellite. We have been paying attention to 2 major elements. One is the what we call the Digital Payload Resource Manager, DPRM, which is basically the interface to how to help the operator to automatically determine how to optimize the configuration, the assignment of frequency spectrum, the assignment of power density, the movement of beam to fit your coverages and all that in a dynamic way. And you have a lot of flexibility in terms of how automatically you want to do that. You can kind of follow a machine learning type approach where you collect enough data, you sense a pattern, then you can program into those algorithms and it will execute those configurations for you. That's a very important part. And then the second part is what we call the processor ground controller, which is basically a window into the configuration on the processor and the payload in general, and how you want to mimic the reaction, the responses before you do anything. Because I think when you have a lot of flexibility, one of the important thing we have to pay attention to is you don't want to do harm by not running through all these thought process before you change anything. And there are so many almost infinite number of combinations of that. So that PGC is also a very key element that is a little bit more intrinsic to tie to the overall design of the processor on board of the satellite. And then as Stuart was mentioning that we are also paying a lot of attention to basically making it a compatible to open standard, like using containerized software approach, using API, so that when we offer this type of overall system together with the satellite and the ground software to a potential customer, we can customize it to a customer that already has a legacy infrastructure we interface with whatever they have already, as well as other new entrants that may need the whole end-to-end solution. So I think those are the elements that we have been paying attention to.
So the beams or the channels start looking just like regular network pipes. Essentially, if you can consider them just part of an overall kind of meta network, and as long as you speak the same language between the interfaces, then it's reasonably
that's right. Standard. That's right. Actually, if you extend it to the next level, right, you can have a system that is tied into other means of closing the link, right? Does not have to go to a satellite. You can actually have a network that consists of satellite as well as other terrestrial, or maybe even satellite in terms of geo and LEO and terrestrial.
Yeah, just a network node.
Just a network node, exactly.
And that really goes to my next question, which was a question I was going to ask Stuart, which is, we've talked a lot about this technology on the satellite kind of pulling the industry, but I actually believe that a lot of this is technology push from the terrestrial networks, because terrestrial networks have evolved dramatically, as we know, over the last 5 to 10 years with these the digitization of the networks and more software-defined networking. Is it a necessity now to follow the standards of the modern network, of the 5G networks, and make sure that we're talking the same, that satellites talk the same language as the terrestrial networks? Is that something we have to do, we have to accept? Otherwise, we can't be a seamless part of the network.
Yeah. So starting a little bit on the last question and moving into this question, I think the answer both Hampton and Francis pointed out is the fact that you got to recognize it used to be you had an FSS satellite that was a bent pipe. So effectively in your network diagram, it was a wire. Now it's an active device. It's like a very large complex network switch in the network. So now it's an actively controlled component in your network, and an actively controlled and managed piece. So that's why when Francis talks about his SDN controller feeding out commands to the satellite control system to control the payload, you have to do that because you need to manage the satellite now as part of the network. It's
I think the key point there is that you said before it was a wire, but the endpoints were also termination points before, right? We only had we controlled both ends, but now we're part of a much bigger network where the endpoints and
well, exactly. So now that we're doing IP data traffic, at one end of the network or the other end of the network is usually some type of other network, whether it be terrestrial, 5G, whatever. And therefore, it's critical that you make it, since you're going to, on almost every service, you're going to be connecting to a terrestrial network of some type. It's critical that you make that network connection relatively easy for them. And, and that's just, you do that by, one, copying their technologies and architecture. You want to make the SATCOM network look as much like a terrestrial network as possible. And the way you do that is, looking at their technologies and architecture, but most importantly, utilizing their standards. And in that way, they can start provisioning and orchestrating services right through the SATCOM network like they can do through terrestrial networks. And that opens up huge opportunities for the satellite industry. Now, that said, the satellite industry does not have the greatest track record about following standards. And but I think that's changing. I really do, because I think the industry realizes that it needs to change. Kratos has been involved recently with the formation of the DIFI organization, which is Digital IF Interoperability Consortium. And it was all about the fact that when you digitize your infrastructure, when you had L-band analog signals, you had interoperability by definition.
Yep.
All of a sudden, when you digitize it and stick it in package, you lost that. So the organization was formed to create a standard to give us that same level of interoperability, and we've been really impressed with the response we've gotten from the industry and the support we've gotten from the industry. So I'll put a little plug that I'll ask people, if you don't know what it is, please go check out our website, diffieconsortium.org, and consider joining the organization, because it's really going to help drive the organization through digital transformation, because you're not going to make it through the digital transformation without standards. I mean, we saw that in the terrestrial industry when it went from 2G to 3G, how it exploded. I know primarily because they've implied standards that allowed interoperability between networks.
Right. And look, as we move toward those standards, we have to think about, and this goes to, I'm going to come back to something else you mentioned earlier. We have to think about what the various players are good at and where they should play, where there's the comparative advantage, right? So where should a satellite operator, what equipment should he own, and what should he lease, and where should he be within this overall network, idea? If we're going to be part of the global ecosystem for 5G or whatever, you have to start redefining your endpoints or your connection points, and comes back to the kind of ground system as a service. If we move toward digitization and SDNs and network virtualizations, and we've got very sophisticated satellites that, as you said, are complicated, are essentially network switches in the sky. Where do we draw the line, and how do we translate, or how do we transition to a ground system as a service for communications architectures? As you said, it's common in the Earth observing world now, but who would the players be? Who should be the players in the ground system as a service? Should it be legacy satellite owners, or should it be like Kratos? And where do the demarcation points come?
So
it's a question for everyone, actually.
Yeah, this is a great question, and I'm actually kind of want to hear Hampton's answer on this, because one of the things when we look at these Ultra HD software-defined satellites, and it looks like a network switch, it's not transponder. They're not transponder driven anymore. So so you have these very wide band amplifiers, you have these very sophisticated antennas, and they're shared resources across all services going across the satellite. So we see that it's going to be way easier for satellite operators to sell megabits instead of megahertz, because it's going to be harder to sell megahertz when you sell that customer megahertz, anything he does is going to impact all of your other operators. And how do you sell, when you're selling megahertz, how do you sell them the flexibility that the satellite has to offer? So like if you look at Hughes, they've solved that problem by they just manage the satellite and they sell megabits to their end customers. And so one of the things when we've looked at that, we see that that's probably going to be the trend. At least that's what we think. And that's why I want to hear Hampton's answer, because of the capabilities of the satellite, because it's not transponderized. We think it's going to drive the satellite manufacturer or satellite operators to sell megabits instead of megahertz, and therefore that's going to set up your demarcations a little differently than they were in the past.
Right. So first of all, I believe the operator actually still have the flexibility. I think the easier way is to sell in terms of bits, gigabits, right? And but if they want to, they can sell in megahertz as well. And the way to do that is what we've been working on is the key is the resource manager, because your resource manager can build in from a software standpoint some of these rules of operation, and then with the help of the PGC, you can define some of these predetermined partitioning of resources. And then once you reach a certain limit, then you can execute or activate some limitation or some other means of operation. So there is a way that you can we can help the operator in terms of selling these type of capacity in a different way, but have a way to manage that as well. So even though it is different from the old way of selling a single transponder and all that, but it's basically it's very doable, but it requires a different set of tools and software to make it happen.
Yeah. Look, so we're almost out of time. I've got one more question I want to bring up for everyone. I'm going to go around and everyone can give their opinion. I think we would be amiss on a panel about technology, space technology, not to at least kind of address the not the 10,000 pound gorilla, but maybe the 10,000 satellite gorilla, the LEO constellations and how they will how they will play and how much they will dominate, and whether the geo satellites will continue to have a future. I have my own opinions, but I won't share them. I don't know who wants to go first. Maybe Hampton, do you want to
Sure.
crack at it?
Sure, I'll go first. I think overall, I believe that the GEO market and the LEO satellite, there are some overlap in the markets that they serve, but they are not completely, mirror image of each other. Okay, so there are some services that, for example, if you want to serve the two poles of the Earth, and obviously LEO will have an advantage because of the visibility and from the coverage standpoint. And if you have a surface that you need short latency, then LEO has an advantage. But GEO has the other advantages that it can cover a large area all at once with a single satellite, and it also has a simpler user terminal to make it work. In general, I think the requirement on these tracking user terminal associated with LEO, it's still not as cheap as they need to be in order to make it the total surface.
Especially in Asia, actually, especially
right.
For the Asian market.
Right. So in short, I believe that both will coexist in some way, and I don't think GEO will disappear just because of the proliferation of LEO. But there's certainly some markets that the LEO will do better than GEO, and that's our view. Yeah.
Do you want to give your opinion, Stuart, and then we'll go to Francis?
Sure. So my opinion very close to Hampton's that. There's absolutely markets where LEOs provide an advantage, basically around latency. And it's hard to imagine that in the long term that a LEO constellation can deliver a bit at the same price point that a GEO can. I mean, it just has some physics advantages. Mm-hmm. And so I think, there's going to be a market for both because the appetite for data is just ever growing. And so I think there'll be plenty of business for both groups. I think there's still some question about the LEO business models and how they'll close. But I think bottom line is the LEO constellations are here to stay and the foreseeable future. And I think they'll both coexist, and I think both markets will actually do quite well.
Francis?
Yeah, so our view is that GEO HTS still will deliver the lowest cost per bit on the satellite. And also the other biggest benefit is the lowest cost of the terminal. So when you go into a rural market where you connect all the unconnected people, the key drivers for the economics to work is the cost of the bandwidth and the cost of the terminal. So we think that GEO will continue to be a critical element in those markets. But we also believe in this multi-orbital approach. That's why if you see that the Jupiter system today can support GEO as well as MEO. We have done demonstrations with live switchover between a Jupiter satellite and the O3b, SES O3b. So we strongly believe in this multi-orbit, multi-transport. There's no one single technology or orbit will address all the requirements, but there are certainly some applications like IoT, possibly cellular backhaul. Mm-hmm. Those kind of application will transition from GEO to LEO because of what Stuart said, it's very latency sensitive. So if somebody wanted to offer an IoT service, for example, if you wanted to offer some services to financial market, like connecting point of sale terminals, they're very latency sensitive. They would probably prefer a LEO service versus GEO. But again, I think it will take a while for somebody to come up with a cost-effective, a LEO terminal to make that happen. So GEO will continue to have a critical role in delivering broadband services and addressing certain other markets, but we strongly believe that eventually, LEO, MEO, and GEO will coexist.
I think that's a fair point. I mean, we through our consulting and other areas, we see a lot of business cases. We also see a lot of the technology development. I do think that the user terminal, there are several interesting technologies in the pipeline that could improve the cost the cost equation for the tracking antennas. But it's still going to be more expensive than a simple geoterminal, without a doubt. I think that my feeling is there is a couple of risks to the geo business or to the geo satellites. I don't think they are. I don't think they're death knells, but there are a couple of risks, particularly for the B2B business sector. So for the B2B applications, there is, I believe, a strong benefit in having a seamless layer 2 interface. I think that being able to be native with the terrestrial networks, be able to interface directly at layer 2 and use the same transfer protocols and the same flow controls and the same HTTPS, the secure HTTP. All of those benefits are difficult to ignore, and the fact is that LEO is just easier to make that work because of the latency and because you don't have you can tolerate the multi-handshake. That's not to say that you can't spoof it with geo, but it is a strong advantage. And I believe that eventually what we'll see is we'll start seeing a strong position in the B2B market for LEO, but it won't be everywhere because of the cost. But I do think in the B2C, I don't see. I agree with everything you've said. Everything everyone said is that the cost per bit advantage in the B2C market and the low cost terminals will mean that I believe in the B2C market that geo is still going to be the strongest position. But we'll see. I think they'll both exist. We'll see which way the hardware goes. But I think it's good for the industry to have all this development. I'm excited to see when Jupiter 3 launches next year, right? Is that right?
Second half of 2022, yes, next year.
Yeah.
And we are really waiting for the launch. Yeah.
And Viasat 3 will launch similar times, I believe, and that's also a gigantic high density satellite. So we're going to see kind of the best of the best go up there, and we'll see how you do against the LEO satellites. Hopefully, it's a good fight. So. Anyway, so I think we've covered all my questions. I don't know if anyone else has something you want to raise, or if any of you have something you want to raise. We've got a few minutes, but other than that, I think I've answered all my questions.
No, I'm fine.
Well, look, thank you so much, everyone. I learned something, which was good, and I think it was hopefully people who are watching this also learned something. That was the goal, anyway.
Thank you very much.
Thank you, Graham.
Thank you very much.
Thank you.
Thank you very much for that, Graham. Thank you also, Hampton. Thank you, Stuart. And thank you, Francis. And thank you very much to Maxar for supporting today's webinar. We do appreciate your ongoing support. If you or your company are interested in sponsoring one of the APSCC webinars, check out the upcoming topics list here at apsccsat.com, the website where you should be watching this program. If you're interested in one of those subjects and you want to get your brand or your company affiliated with that, please just do get in contact with us. Likewise, if you see something there, if you don't see anything there that you're interested in, but you're interested in presenting a webinar, come let us know, and we'll figure out what we can do to work with you. Likewise, check out apscc.or.kr, which is the main APSCC website. If you're interested in joining the association, please, you'll find all the information that you need there. Thank you once again. We look forward to seeing you in future webinars, and take care.